Are we gonna have any bonus this time? Like first time? Like calculus barrels?
No. I doubt it. All these homework cards I'm giving you when I go around those.
I told myself I was gonna get a perfect grade on this Thursday.
That's already shown.
I completely forgot about Thursday.
All right, so let's take a look at just to familiarize ourselves with the area stuff. You know, we are going to get back into a little bit more of a groove here, which is a good thing. So, you know, next week, so we can kind of. But even then, things are broken up a little bit. We have assignments, but we kind of mix in some longer term assignments with daily assignments, right? And so you just gotta stay organized with it and keep up with it as we try to just keep going back and spiral back to our review for our finals, and as well as these last few new things we're adding in as well. So I want to look at like 20, 21. You had 15, 21, 23. These were problems that you were supposed to draw sketches. So that's one of the things I was looking at for the few of you that did this one. So we probably had better talk about it. So let's look at number 21 here for sure on page 409. Actually, probably over onto page 410. But when you're just supposed to do this area. Now it says f of y equals y squared. What does f of y mean? It's another name for f of y. X, right? Just like f of x is the same as y, f of y is the same as x. So when they say f of y equals y squared, they're saying x equals y squared. And when they say g of y is y plus 2, they're saying x equals y plus 2. Now you have two ways to graph these. One way is to just solve for y. So you can solve for y here. You get y equals plus or minus square root of x, and hopefully you know that that means the top and the bottom half of the parabola. And then you could solve this one for y and get y equals x minus 2. And so that's a y-intercept of -2 and a slope of 1, and it kind of goes like this. So it's this region right here. Okay? Now, what type of strips would work best in that region? What type of strips would work best in that region? Horizontal. Because horizontal strips would lay this way, where the right edge would be on the line and the left edge would be on the parabola. Vertical strips would be, you'd have to split it into two parts, because your vertical strips over here would hit the parabola on the top and the bottom, and then vertical strips here would hit the parabola on the line. So you'd have to split it into two parts, which is certainly doable, but it would be nice to just do horizontal strips here. Now, the other thing that you can do to graph those, and I showed you this the other day, is on your calculator. You can go into your menu, and you can go to graph entry, and you can go to relation, and you can see I just typed in x equals y squared, and I typed in x equals y plus 2. Okay, and I just typed those in, and I get these graphs right here. Now I have went ahead and changed my window a little bit and so forth, and I actually went on here and I found the intersection point. I let the calculator find the intersection point for me. Of course, the other thing you can do is you can just do a solve. You can just say, where does, just solve, where does y squared equal y plus 2? Where are the two equations equal? Because sometimes you have to do that. You have to find where they intersect. Okay, and so that's at y equals -1 or y equals 2. Now keep in mind that's the y values. So here was y equals 2, and here's y equals -1. And then, of course, you get the x values with it. Yes?
You get the calculator put out the intersection point.
What I did there is I just clicked on this graph right here to highlight it, and I went over here to analyze graph and intersection. And then what it asked me, it said, what's a lower bound? And so I just went below the intersection point, and then what's an upper bound? And I click, and then it found it and just put it there. Now put another one there. Then you can drag it away. But it'll put it on there. But so that's something you can do with that. Or like I said, you can just do a solve. You know, because to be honest, a lot of times you're not going to graph them. Like on the AP test, a lot of times they give you the graph, and as we're going to see some today, and then so you don't really need to graph them, so you probably just do a solve on your calculator most of the time. But anyway, you have that option. So if we were to look at this one, so this is number 21 there. So if we're going to go ahead and draw in a strip, okay, we want to do the area of this region. Well, we want the length of that strip times the width. Now, what's the width of this strip right here? What's the width of this strip? dy, right? When they're horizontal strips, the width is the delta y or the dy. The length of the strip is this x-coordinate subtract this x-coordinate. Well, what is this red x-coordinate right here? What's the red x-coordinate? No? There you go. Y plus 2 right there. X equals y plus 2. So the red x-coordinate is y plus 2 minus the blue x-coordinate, y squared, and then times the width. So I want you to really understand this. So we got the length of the strip times the width of the strip gives you the area of the strip. And what's the integral do? Adds up all the strips. And it adds up all the strips from -1 to 2. -1 to 2. And that would be your answer to number 21. And in the answer book, that would be, and you should have had, they've got 9 halves, 4.5, okay, for number 21. Okay, so we can't forget about these basic just area graphs. We did the Lemon Lab, and we were talking about volumes, okay, which we're going to get into the rest of today, but don't forget about just plain old area problems where we just use the integral to add up the areas of the strips. Okay, we're going to talk a lot more today about strips. Nope, not here today. And so let's take a look. Go ahead and get your notes out. And so this is the, and then we're going to look at those other homework problems too, though. I mean, the 419 we're going to look at here in a minute. So what we came up with on Wednesday with our lemon lab was finding the volume by adding up slices. So you guys slice those lemons into 6 perfectly symmetrical, equal slices. And then we thought about adding those up to get the total volume of the lemon, right? And then we said, but we can do 100 slices, 1,000,000 slices, and infinite slices, and we could get the volume by adding up those slices. Now, how do you get the volume of a slice? Well, you take the area of the slice times the thickness of the slice, but the thickness goes down to nothing. That's the dx. And that's why that gives you volume. So the area of the slice times the thickness of the slice, and then the integral adds up all the slices, and that gives you the volume of the solid, okay? So this works for any solid where all the slices are the same shape. Now, it might be different sizes, right? Some of those slices were littler than some of the other slices, right? But they're all circular slices. Okay, so here's a couple of solid pieces I have right here. We talked about an engineer and you're designing some sort of a part or something, maybe something like this. And there's some mathematical, almost looks like a little sine curve or something. This looks like maybe a little parabola in here. But some sort of mathematical equation you could make that would generate these solids. Now, these would be where you would revolve and you would create these. You can see these would all have circular slices. If I was to slice this thing and just start cutting through here, I'd have slices. Now, the cylinder part, they'd all be the same size circles, but here you'd have some littler circles in here. Just like in here, you'd have some littler ones. They get bigger. Okay, but these are circle slices. So this is what we were looking at. With the lemon. And so today we're going to make a list of slices. There's 5 different slices that I'm going to have you have to deal with in problems this year. Okay, when it comes to volume problems. And these are the ones that you would commonly see on the AP test. Now, sometimes they throw in a different one than the 5 we're going to look at, but it's definitely one that you should be able to think your way through and be able to do. And we'll look at some examples of that as we go along. Okay, so one type of slice would be a circle. slice. And of course, what do we need to know? We need to know the area of a circle. Well, that's pi times radius squared. And a circle would look something like this, right? A circular slice, like so. Try to make it look a little three-dimensional, maybe. With a little thickness there, I don't know, whatever. But anyway, so like our lemons, our lemons had circular slices, like these blue objects here, they would have circular slices, okay? Now, that brings me to our little toy here, okay? If you looked at this, now pretend that these rings, pretend that these were all solid all the way through, okay? And pretend this was just one object, right? And then I took my knife out and I sliced it into 5 slices, right? Well, there's 1, there's 2, there's 3, there's 4, there's 5. What shape is this? The washer. Remember we looked at one of those, didn't we look at one of those on Wednesday? We looked at those pictures. This would be that washer or donut or ring or something like that. So these slices are similar. They're circular, but they're not circles. They're, like say, a washer or a ring. I can tell the look on his face. Just good. All right. So anyway, let's add that to our list of slices, and we're going to talk about how to a washer or a ring or whatever, okay? And we'll talk about, well, you guys tell me, what's the area? What's the area of a ring? What's the area of a washer? Yeah, and again, when we say a washer, we're talking about something like this, right? So we're talking about this shaded area here, right? We're talking about this shaded area and give it a little bit of thickness here, maybe. Okay, but we're talking about that. Well, that is big R, that would be pi times big R squared minus pi times little r squared. A lot of times you use big R for the big radius, use little r for the small radius, okay? And so, or your outer, so you have an outer circle minus your inner circle. Now, what we're going to do instead is we're going to factor out the pi. So I'm going to put it here. We're going to factor out the pi and then just do big R squared minus little r squared like that. Okay, because that way when we put it into our integral, we can pull out the pi. And that's what we're going to do. Because remember back on this page, right, for our volume, what we want to put in here is our area of our slice. So if our slice is a circle, we want to put this in the integral. If our slice is a washer, we want to put that into our integral, right? So whatever goes into our integral here is the area of the slice we're dealing with. And so we're going to make a list of slices here with their area formulas, and that's what's going to go into the integral. Okay, now I'm jumping a little bit ahead here because let's take a look at our homework here that we had for Wednesday. Okay, so these were just real simple regions, so we're going to go through this pretty quickly. But we were going to take this region and we were going to revolve it around the x-axis. Well, now I'm not always going to draw this. I'll do it for a couple of them today. So if we would revolve that region around, we can see, oh gosh, that's bad. You can see we would basically have a cone, right? Kind of a cone tipped up. That if we revolve this region, we would have a cone shape. And what would our slice be? Our slice right here would be this circle. So this would be our circular slice. Think of it this way. Here's the x-axis right here, my finger. We set the strip right here. And when we revolve that, you can see it creates a circle, right? And so that's a circular slice. Now you're going to have bigger slices on this end, and you're going to have littler slices here on this end. But we want the integral to add those up. But the key is they're all circles. So pi r squared. So what is the radius of that circle? It's the strip, right? There's your radius right there. The strip is the radius. So all we need is, and this is why top minus bottom and right minus left is so important. All we have to do is take the top y value, which is negative x plus 1, minus the bottom y value, which is 0, and that is our radius. I really want you to get in the habit, you'll see why today, that really get in the habit of writing out that radius, right? And so now we do our integral, and so it's going to be pi, it's going to be our radius squared times our thickness, and then the strips, the slices go from what to what? What was it? 0 to 1. And what'd you get for an answer on that one? Pi thirds? Pi thirds when you type that in. Pi thirds would be that. Now, it is a cone. It's a cone of height 1, and this up here is 1 as well. And so it's a cone of radius 1 and height 1, and if you remember from geometry, not even geometry, remember from related rates, when we did piles of sand that were cones, 1/3 pi r squared h. You put a 1 in there, you put a 1 in for the radius, you put a 1 in for the height, what do you get? You get 1/3 pi, right? The volume of that cone should be pi thirds, 1/3 pi. Now, since that's geometry, we can get that volume pretty easily. But it's nice to know that that integral works as well. Gives us the same answer. Okay, let's go to this one. Okay, going to this one, same thing. We're going to have our strip right here. We're going to revolve that region around, and sure enough, we're going to end up with this slice right here. Right? You don't have to draw that slice every time, but just understand that the strip is the radius of that slice. And so all we have to do is top y value, which would be that curve, minus the bottom y value, which is 0. So that's pretty basic. And simply pi radius squared from what to what? 0 to 2. 0 to 2 for a final answer of what? What is it in terms of pi? 256 pi over 15. Okay, go to number 4 quickly here. We got radius. We revolve it. Creates that slice. You got a radius, top y value x squared, bottom y value 0. So the circle slices pi radius squared from 0 to, what is that, 1? 0 to 1. So easy. Answer of pi fifths. Okay, then we get a couple that are horizontal. So now we got to, right, use what we learned about areas. This time we're going to take this strip. This time we're going to slice it this way. Okay, when you've got a vertical axis of revolution, then you've got to slice perpendicular to that. And so you're going to slice horizontally. And so, again, the strip is the radius. Okay, the strip is the radius. So, put our strip in here. This time, the slice looks like that. The slice looks like that. Okay, this is still our radius, but it's right minus left this time. Well, what is this right? What is this x value right here? Square root of y. You've got to solve this for x. The right half here is square root of y. The other half would be negative square root of y. We don't have that. So it's square root of y minus 0 is that radius. So integral pi radius squared. Strips go from 0 to 4. Just like that. Okay? And answer on that one, 8 pi. And the last one, again, we're revolving around this, so we're going to go this way. Here's our slice like that. It's a circle. The radius is this y value. Now, you really do need to solve this. This x value minus this x value. So you really do need to solve this. So you get y squared equals 16 minus x squared. Move your x squared over to here. Subtract your y squared over there. Because of the symmetry of this shape, it does give you the same equation, so it's not a big deal. But we got to take this x coordinate, which is root 16 minus y squared, minus this x coordinate, which is 0, and then our integral pi radius squared, and then from 0 to 4. Now, you could have set that up with x's and not thought about your horizontal strips and got lucky because it is, this is a sphere. This is a quarter of a circle. If you revolve it around here, you get a half a sphere. A sphere is 4/3 pi r cubed. And so half a sphere would be 2/3 pi r cubed. The radius is 4. 4 cubed is 64. That'd be 128 pi over 3. Just using geometry formulas, we can tell that this will be half a sphere. It'd be 128 pi over 3, which I think is what you get when you do this. Okay. All right, so those are the simplest volume problems, the ones where the axis of revolution is right on the axis and there's no empty space, that radius revolves around and you have that. Okay, let's do this one together now. Let's go ahead and write this one in your notes. So here would be the directions. The directions would describe your region. So the directions would say, okay, let region R be bounded by y equals square root of x, y equals 0, which is the x-axis, and x equals 4. Okay? So that would give us this red region right here. Okay? Bounded by those three pieces. So you need to be able to draw these. Okay? Then it would say, find the volume of the solid when that region is revolved around the line y equals -2. Okay? Now, this, I think, is the picture I showed you the other day. Pretty much. Right? What is your slice going to look like when you make this revolution? Cody's got it, right? They're right there. Now, let's take a look at that picture. Oh, oops. Not supposed to see that. Let's take a look here at, okay, so we take this region and we revolve it, and there it is, right? You have, because remember, it goes around the axis of revolution. So, now my question to you is this. Here's your strip. Everybody look up here now. I know you're drawing your picture and stuff, but here's the strip. Is that the radius of the washer? It's just part of it, right? Is it even an amount we care about? No. So that's a change. We're so focused on the strip that we have in there, and we've used that now that changes. So we got to talk about this, because it's like this. If here's my axis of revolution here, here's what we have going on in this problem. We got the strip up here, and we revolve it, and look at that empty space in there, right? You can see how that creates that washer. Okay? Well, we have to draw the radius. We need this formula. We need this formula right here. We need big R and little r to put into our integral, right? Well, where does big R come from? It's got to come from the center. And where's the center? The center is your axis of revolution. Here's your center. So big R has to go from here all the way up to the curve, and little r has to go from here to the inside part of the washer, right? So when we look at these, basically what we have to do is draw two new strips. This is not a useful strip at all for this problem. Here's our slice. Now, if I was you, I wouldn't be drawing this, but it would go way down here like this, and then it would go, down here like so. That's our slice right there, right? So what we need is our big R would be from here up to here. So go ahead and draw that in your picture. And then little r would be from here to here. So that'll be the biggest thing one of the main things we have to really practice on our homework today is this big R and little r thing. So we have to recognize, do we have a washer? Is there empty space in the problem? And if there is, then we have to be able to draw big R and little r. And where people run into troubles, they don't know where to draw it from. Remember, it's from the center. And the center is the axis of revolution, because you revolve around the axis. The axis of revolution is the middle, the center. Okay, so let's write that down. Now, here's where it becomes really important to write these out there. So what's big R in this problem? Square root of x minus -2, which turns into square root of x plus 2, right? It's the top y value, square root of x, minus the bottom y value, -2. Okay, and what's little r? Because it's 0 minus -2, right? It's this y value, 0, minus this y value, -2. Now we can do our integral. pi on the outside. Now I'm going back to this formula here now, right? Pi on the outside, and then big R squared minus little r squared. Okay? So I got pi, and then I got big R, which is square root of x plus 2. So we got to be really careful about parentheses. Minus little r, which is 2 squared. And then it goes from what to what? The slices go from 0 to 4. The slices go from 0 to 4. Okay? All right. So, and then you type that in and, get your answer. But so where you got to be careful in these problems is because when you're doing just a regular circle where there's no empty space, it's pi times radius squared. So it's the whole radius squared. In this problem, it's each radius squared. So it's big R quantity squared minus little r quantity squared. Sometimes people tend to do big R minus little r and then do all of it squared. They can't do that. It's big R squared minus little r squared. So you got to do the formula correctly. All right. Last thing then that we want to talk about is what other slices can we have? Well, those two that I just gave you. Okay, so back to our notes here. These two here are often called our solids of revolution. These are often called the solids of revolution because anytime you revolve a region, the very act of revolving is going to give you circular shaped slices. So they're either going to have empty space, which would be a washer, or not have empty space, which would be a disc or a circle. Sometimes that's called a disc or a circle slice. Okay? All right. So what other types of regions could we run into? Okay? What other types of shapes could we have that have slices, but they're not circular type slices? They're other shapes, right? Okay? Well, here's one right here, and I think I showed you this the other day too. But, so let's take a look at a problem like this. Now, first of all, there's a couple of problems we're going to do here in a minute once we get done with this. Read part C right here. Read problem B, and then read problem C. Read problem B and then read problem C. Okay, so in problem B, it talks about rotating or revolving the region. Okay, so you're going to have that, what we've been talking about here. But then you read problem C and it sounds totally different, right? The word revolving or rotating is not there. It says that this region is the base of your solid. So what that means is it's like the bottom of your solid, okay? So that's a circle, right? We got a circle that's the bottom of our solid here, okay? So this is the bottom of the solid. Coming up off of your paper is the solid. Okay, so part B was taking this and revolving it up around this line up here, y equals 4. So we're going to take this region, revolve it around, and create a solid. Now in C, we're going to let this be the flat base of the region, and coming up off of here is going to be what shapes? Squares. Each cross section is the same as slice. We're going to have squares coming up off of here. Now, there can be little squares here because it'd be like the end of your lemon. The little slices at the end, the fat part of the lemon were bigger slices, right? Same thing here. The fat part of the region here, we'd have bigger squares coming up. Here, we'd have little squares coming up, okay? Now, to try to give you a picture of this, show you this problem here. So this is the base of our region. So we kind of lay it flat so you can kind of see it. And we're going to have slices in there. You can see in the fat part of the circle, you've got bigger squares. And down here in the narrow part of the circle, you've got smaller squares. Okay? And so the solid would be this. Did I show you this the other day? I can't remember. Okay? The solid would be this right here. okay? And so it would have, right, there'd be your squares in there. You got these edges coming up along here because that's the corners of your squares, right? And, so it would look, there would be the different squares. You get to the fat part of the circle, you got bigger squares. Coming out here, you got smaller squares, okay? Very similar here. Very similar here is this, this problem right here. Nope, wrong one. This problem, okay, lay that flat. So you take that region, lay it flat, and now you imagine the squares coming up off of the page there. Okay, and again, in the skinny part, when you're in the skinny part, you got smaller squares. Okay, so we got squares. So what is our strip? What part of the square is the strip? Well, it's just one side of the. I mean, what's the area of a square? What's the area of a square? It's a side square, right? And in our integral, what do we want? In our integral, all we want is the area of the slice. Well, if our slice is a square, the only thing we want in here is the side square. Well, for a square, right? Look at that right there. That's the strip. That's this strip right here. Top minus bottom, isn't that going to be one of the sides of the square? So all we have to do is take that and square it, put it in our integral, and we'll have it. That's what we're talking about. So this isn't a revolving type solid, but it still has slices. That's the key. We're using the integral to add up the slices. Here our slices are squares. Our slices are squares. Okay? All right. So let's take a look at our notes here, and let's write that in here. Let's write that in as one of our slices. We could have a square slice. Now, what's the area of a square? It's just A equals S squared. And again, what's a square look like? It looks like something like this, maybe with a little thickness added to it. But it's just, right? And S is just a side square. So that's all we need. So our strip now will represent the S, the side of a square. Okay, so now you won't have the advantage. You won't have the advantage of having, the three-dimensional part of this. So what will you do? You'll take a problem like this and you'll say, okay, I'll just put in a strip. Okay, they put in a bunch of strips, but I'll just put in a strip, and that strip is going to be a side of a square. Again, let me show it to you again. Okay, these strips, if we rotate it, right? Just look at it. Those strips right here, these strips right here is one side of the square that's coming off the page. Think of it like, let's lay it flat here again. Oops. Reset, there we go. Okay. So if I draw in a strip, perpendicular to the x-axis, it says, just imagine this is a square. So boom, coming up off the page is a square. That's what we got. Coming up off the page is a square, where this is one side of the square. Here's a square coming up off the page. So what would be the area of that square? Well, this is a radius of 2. So that would be y equals plus or minus square root of 4 minus x squared. So the top y value would be positive square root 4 minus x squared. The bottom y value would be negative square root of 4 minus x squared. That would end up being 2 square root of 4 minus x squared. That would be our s. That would be our side of our square. And so our integral would simply be that square. S squared. That's the area times the thickness. And then we would add those up from where to where? Negative. Strips would go from, it's -2, I think. -2 to 2. And that would give it to us. Again, this in here is just the area of our slice. So if we have a circle slice, what goes in here? pi r squared. We have a washer slice, what goes in here? Pi times big R squared minus little r squared. We have a square slice, what goes in here? S squared, right? Just the area, that's it. All right, so let's go back and let's just do this problem here real quick. This one, let's finish this one we were just reading about. So, now this says F is the parabola, so this would be F right here. This one would be f of x. This one would be g of x, which is our cosine. Now this is from the 2013 AP test. It is a no calculator one. Okay, so we'll talk about that here just real quickly. But okay, so let's look at B. So B says write but do not evaluate an integral that gives a volume when you revolve this around y equals 4. Well, here's y equals 4 right here. Okay? Now we're going to revolve around that. So here's my strip right here. What is that strip? Huh? Well, right. Yeah. Oh, yeah. Yeah, this strip is g of x minus h of x. And actually, I shouldn't skip over part A. Part A says find the area of the region. So wouldn't we just do that strip, right? We just do g minus f. Right? Now, you would have to actually do that one, but if we were doing A, it'd just be the integral of g of x, and you could actually just write g of x, f of x. You don't have to write them all out. And then that would be from what to what? 0 to 2. Now, for this one, you'd actually have to work that. So you're going to have to do the antiderivative of this, right? You're going to have a 1/4 pi or pi force. What do you kick out if you do the antiderivative with a pi force sitting in there? What do you kick out? 4 over pi, right? 4 over pi. You kick out a 4 over pi. The antiderivative of that would be 4. The antiderivative of cosine is sine. You'd have pi force x, and you would kick out a 4 over pi, right? That'd be the antiderivative. That would be good practice. Matter of fact, this might be one of the packets I give you. So you write this down is fine, but I'm probably going to I may give you this packet later anyway to practice as we get farther down the road here. But anyway, so this is a no calculator, so you would have to be doing these antiderivatives, plugging these numbers in. So there's quite a bit of work to be done in part A because of that. Here, all we have to do is do the integral. So let's do this in B. So now back to B. What kind of slice do I have? If I take that region R and I revolve it up here around here, what type of slice do I have? Isn't it a washer? There's empty space right here. There's empty space right here. So it's a washer. So do I want that strip? I don't want that strip at all, do I? What strip do I want? I want big R and little r, right? See how those are big R and little r? Remember, R comes from the center. This is the center. We're taking this region, revolving it around. So big R is the long radius, the big radius, the one that goes to the outer edge, and little r goes from the center to the inner edge. Okay? And so, what is big R? 4 minus f of x, and that's how I would write it. 4 minus the parabola, and little r would be 4 minus g of x. Top y value minus bottom y value. And now what would our integral be? Don't forget the pi. 4 minus f of x squared minus 4 minus g of x squared dx from 0 to 2. The strips would go from 0 to 2. And then you would just leave it. You'd be done for part B. Okay, let's go to part C. Part C. The region R is the base. Each cross section is perpendicular is a square. Now the red strip would be important, right? Now the red strip is important. Now the red strip is a square coming up off the page, right? That's the picture we were just looking at a little bit ago. The red strip is one side of the square. So I would write down S equals, for my red strip, it'd be what? G of x minus f of x, and my integral would be g of x minus f of x, that'd be s, that'd be the s, that this red strip is one side of the square, and we would square that, give you the area of the square, times the thickness, that'd give you the volume, the integral adds it up. Do I need a pi in front? No, don't want a pi in front, right? It's a square, it doesn't have pi in it. Integral goes from what to what? 0 to 2. Right? So we got the red strip is one side of the square coming up off the page. We square that. That gives us the area of the square. We do the thickness, gives us the volume of the square. The integral adds up all the square slices. All right. So what other kinds of two slices could we have? So quickly, just to finish up here, on our list of slices, I got two more we could have. We could take this same base here, and instead of squares coming up off of the page, we could have equilateral triangles. Now, we can have all kinds of shapes, but we're going to limit. I'm going to limit it to just a few that you need to know. So what would a shape, what would a solid look like here that had equilateral triangle slices? So every time we slice this, we would get equilateral triangle slices. It would look, I don't know, is that like a conquistador helmet or something? I don't know. But it's, right, it's got equilateral triangles coming up off the page. So what do we need? We need the area of an equilateral triangle. Now look at your strip here, right? Look at your strip. Here's a strip right here. Okay, here's here's a strip right here, right? Well, what is that strip? It's one side of your equilateral triangle. And they're all the same in an equilateral triangle, aren't they? Here's the area of an equilateral triangle right here. Square root of 3 over 4 times s squared. That's real easy to figure out. It's a 30-60 triangle. Drop an altitude in there. It's got 60-degree corners. 1/2 s times square root of 3 over 2s is your base times your height. Well, s is your base. Square root of 3 over 2s, because it's crossing the 60-degree angle, is your height, and then times 1/2. You get square root of 3 over 4 times s squared. Okay, so we're going to add that to our list of slices. Equilateral triangle. The area is square root of 3 over 4 times s squared. And so here's your picture, like so, right, where s is the sides, okay? So think about that, what we just did. It would be exactly the same answer, except outside the integral, you'd stick a what? Square root of 3 over 4, right? You would do your strip. You would do your strip. Here, the strip was a side of the square. In this one, the strip is a side of the equilateral triangle. So all you put in your integral is the strip squared, and then stick a square root of 3 over 4 out front. Very easy. Okay, the last one is what happens. Here's a different region. Here's a different region now I've made up here, okay? And this time we'll do horizontal, just as an example, we'll do horizontal strips, horizontal slices. And this time our slices are going to be semicircles. Semicircles. We're not revolving. There's no revolving happening with this solid. But our slices are semicircles. Well, here's your strip right here. Right? Here's your strip right here. What part of the semicircle is the strip? The diameter. So this time, when we do our strip, when we do our right minus left, it will be d equals something, right? Now, what's the area of a semicircle? What's the area of a semicircle? 1/2 pi r squared. Now, here's the problem. The area of a semicircle has an r in it, and our strip is going to be diameter. So how can we do that? Okay, we could divide it by 2. Now, this is what I used to do for several years. I just got so tired of people getting confused. I thought, okay, there's a better way. But yes, we could do this. We could take our diameter, so we could go right x coordinate minus left x coordinate. So we could go right minus left, get this equation, and then we can divide it by 2, but then that gets messy. And then we could stick it into here. And then we would square that, do a pi, and then put a 1/2 here. Now, here's what I found out people kept screwing up. You would do your right minus left. You would take it times 1/2. Then you would put it in here and then forget to do the 1/2 there. because you already did a 1/2, and they forget that 1/2, and why am I doing 1/2 twice, and blah, blah, blah. So I decided it'd be better to just rewrite our area equation. So what's another name for R instead of R but uses D? What's the equivalent of R? No, that still uses R. 1/2 D. So let's take R out of here. Let's take R out of here and replace it with 1/2 D. Now, let's square that. 1/2 D squared, that'd be 1/4 D squared, times that half. This would be 1/8 or pi-8 D squared. And let's use that as our area of the semicircle. That'll just make it easier because our strip is going to be D. Remember, coming up off the page are semicircle. So our strip is going to be the diameter of the semicircle. So we'll just stick it into there. Pi-8 D squared. So in our notes, last slice, semicircle, area equals pi-8 D squared. So a semicircle slice look like this. Right? Something like that. A little bit of thickness to it, whatever. And there's your D right there, right? And that'll be your strip. And so once you get your strip, just like up here, once you get your strip, you'll square it. So really the equation is very much like these. All three of these are pretty much the same. If it's a square, you take your strip and square it. If it's a triangle, you take your strip and put this in front. And if it's a semicircle, you do your strip and you put a pi-8 in front. Right? You take your strip, you square it, and you put your pi-8 in front. So those are all very similar problems. Okay? All right, for your homework, let's take a look at doing on your assignment sheet here. So there's the line that says LH, page 419. It says 13, that's got a star by it. I don't really remember why I have a star by it. I know it's got multiple parts, so that might be why I did that. But so does 15, so I'm not sure why. And then we're going to do one from page 421. Actually, some of those others move over onto page 420, so it's the same assignment. I'm not sure. But let's go ahead and do 49 ABC, which has some of those circle and equilateral triangle slices as well. So let's do those right there for Monday. Okay, if you do have some extra work to do on those other two packets, and you probably should get doing that. All right, and so let's work hard on this now. I know it's Friday, but let's finish good here with a half hour. 13's got like 4 parts. The answers are here. They're all set up nicely for you, so it's a really great check on 13 and 15 to really make sure. A lot of them have the big R, little r thing, which is probably the hardest thing we have going with these is getting that all for sure figured out. So 13, 15, they're all drawn out real nice and got the answers here. Okay, so let's work for a while here and make sure we're getting those figured out. Which packet?
Wednesday.
Yeah, that's what we were talking about at the beginning of the